Hey, welcome to another session of the Flipped Classroom for AP Calc. This is session 37. We're going to talk about the washer method. It's a pretty easy method and it's a short video, so here we go. Let's say the region that we're revolving around an axis does not border or cross the axis of rotation. Then what will form is a hole in the resulting solid. So instead of having let's say a Bismarck, we would have a donut, okay, where the hole would be, you have to take that volume away from the solid of revolution. We would denote the radius of the hole as lowercase r of x, or whatever variable you're using, x or y, and the outer radius is denoted by capital R of x. The washer's area then, okay, the cross-sectional area, A of x, is given by pi capital R of x squared minus pi little r of x squared. And the volume would just be the sum of those areas times the width of the subinterval, okay? So it would be the integral from A to B of pi capital R of x squared minus pi capital R, little r of x squared, okay? Here's the steps and a sample problem. Okay, let's say we've got a region that's bounded by y equals x squared plus 1, which is a parabola denoted by this red curve here, and the line y equals negative x plus 3. The area that is bounded by these two curves, okay, I'm moving the mouse over it now, is the area that we want to rotate around the x-axis. So you can see that we're going to have a hole here, okay? The radius of that hole would be denoted by this blue rectangle, and the actual solid that we're going to get would be the yellow. So really what we want to do is the outer radius would be the blue plus the yellow. That would be capital R of x. And we want to subtract the little r of x, that area or volume, from the big R of x, okay? So the step, now be careful that you need to subtract volumes, areas, not just the linear radius. That will not give you the correct answer. So you want to subtract pi capital R of x squared minus pi little r of x squared, the cross-sectional areas. The next step is to find the intersection points and determine the lower and upper bounds of integration. So as you can see from the curve here, the one intersection here, let's call it A, is at -2, and the other intersection, let's call that B, is at 1, and those will be our limits of integration. Okay. The final step is just to integrate pi capital R of x squared minus pi little r of x squared from A to B. So as I said, A equals -2, B equals 1. So capital R of x in this case can be denoted by the function, okay, because this is all capital R of x, and that would be negative x plus 3. The little radius, okay, as we rotate this solid, would be the parabola's value, which would be x squared plus 1. So we set this up as pi times the integral of negative x plus 3, the big radius, squared, okay, it's pi r squared, don't forget, minus the little radius, which is the whole, x squared plus 1, that quantity squared, dx, from 1 to -2. And that equals, when we integrate it, negative pi times negative x plus 3 quantity cubed divided by 3 minus pi x to the 5th over 5 plus 2x cubed over 3 plus x, all evaluated at 1, -2. And when you do the math here, which I assume you can do, we get the volume equals 117/5 pi units cubed. So basically we're subtracting the whole from the whole, H-O-L-E, from the whole solid, W-H-O-L-E. Okay? Alright. Sometimes we're not going to go around the x-axis, we're going to go around a vertical axis, in this case y. So let's say we've got the region bounded by y equals x squared and y equals 2x. in the first quadrant, and we want to revolve it about the y-axis. Find the volume. Okay, so this clearly is y equals x squared. This is y equals 2x. Here the trick is we're going around the y-axis, so we need to solve these two functions, solve them in terms of y. So y equals x squared becomes x equals the square root of y. We're going to call that the big radius, r of y, and y equals 2x, when we solve that for y, we get x equals y over 2, which will be the little radius. Okay, so the big radius here is the yellow plus the blue. The whole, or the little radius, is just the blue, and that would be y over 2. So now we're going to integrate with respect to y, and of course our limits of integration will be on the y-axis, and those will be the points of intersection. Okay, the points of intersection right here, 4, and down here, 0. So what we want to do is we want to take the integral of pi times square root of y squared minus y over 2 squared, remember that radius has to be squared, and integrate that from 4 to 0. What we get is pi times the quantity y squared over 2 minus pi times the quantity y cubed over 12. Okay, evaluated at 4, 0. When we do that, we get the total volume of this solid of revolution to be 8/3 pi units cubed. What we're finding is the volume of this solid when it's revolved around the y-axis. This area here is our hole. Okay? Practice. Let's work on page 426, numbers 31 through 51. Peace.